Hello and welcome to the Omnex webinar, Best Practice in SYS Processes for Automotive SPICE. Today's presenter is Nikhil Unnikrishnan. Nikhil is Omnex's project manager for EV/AV project. He is a consultant with broad experience ranging from working in automotive customers involved in design and development of hardware, software, mechanical systems, and components. He is an INTAX certified competent assessor for automotive SPICE, and he has worked in organizations to analyze process deficiencies and drive improvement by implementing best-in-class processes and practices conforming to internationally recognized standards, including Automotive SPICE, ISO 26262 for functional safety, ISO 9001, and IATF 16949. During this webinar, if you have any questions for Nikhil, please enter them in the Q&A box, and we will get to them to the best of his ability at the end of the webinar. The webinar is being recorded, and someone from Omnex will reach out to you after the webinar with how to access to the recording. All right, Nikhil, you can take it away.
All right. Thank you, Miles, for the introduction there. Good morning, good afternoon, good evening, wherever you're all joining from. Thank you for joining us today on this webinar as we explore some of the best practices within systems engineering that I will be explaining using the SYS processes within Automotive SPICE PAM 3.1. All right, with that, let me start sharing my screen, and welcome to all. So just so that you know, with the agenda of the webinar, and also before I get into it, what we were planning to accomplish in this 1 hour. One of the examples we highlighted is how FMEAs have been used for a few decades right now. So we're going to look at some of the similar best practices in the industry and see how that can support systems engineering and thereby help you meet the SYS2, SYS3, SYS4, SYS5 processes within Automotive SPICE. And as we go through this, please document any questions you have in the Q&A box, and I'll get to them at the end. Okay. So I'll start off with a very brief intro into the systems engineering thinking, and also what are the typical challenges we encounter as we try to implement that. Further, we explore what are the best practices to consider in system requirements analysis, and next into the systems architectural design, and lastly into the systems integration and qualification level testings as well. And finally, we will conclude. With that, let's get into definition of system. So with the definition of a system, typically, what we've seen is a product being looked at as having a system, and then you have a software, and then you have a hardware, and then let's say you have a mechanical system. And how INCOSE goes about defining system as a system is an arrangement of parts or elements that together exhibit a behavior or meaning that the individual constituents do not. So for example, the mechanical alone cannot function without what the hardware has to support it with, or the hardware cannot do what it has to do without what the software needs to support it with, to get things executed. So together, the three of them make the system possible, in other words. And as you get into more complex systems, we're talking about the product having a system, and then it having further subsystems. And then from there, you have, again, each subsystem having its own software, hardware, mechanical, software. And as you can see the diagram illustrating that. So the systems engineering, really, we're not talking about restricting it directly from the system to the software, hardware, mechanical. You could have multiple levels of system, subsystem, subsystem before you get into the individual software, hardware, mechanical. So how does an organization developing a very complex system that could have a lot of subsystems still practice some of the best practices in systems engineering while conforming with SYS. That's a typical challenge that we encounter. So let's talk about that. So organizations going directly from stakeholder requirements to the individual domains, such as hardware, software, mechanical, chemical, etc., they are going to lose out on the advantage of the systems engineering thinking and its principle. So let me explain further. So if you have different subsystems that are being developed in, let's say, different design centers across the globe, and then they're all coming together and then to be put into the super system or the main system, how can we ensure that they all still connect and talk to each other the way it should? So as we get into the next bullet here, we're talking about the missing level within the new product development. So where organizations do not practice this systems engineering thinking, they just have, for example, the software thing, development team doing its own thing, the hardware development team doing their own processes, and then the mechanical team doing their own processes. But there's nobody helping put all of this together in one single place. So when you implement systems engineering, it helps you define what the design and development team within each domain must do when you decompose it from the system and then into the specific domains. And also this group will help bring together the results of these individual engineering domains into one single platform. That is one single place where everything is coming together. And finally, as you're talking about the V&V model and your testing and your verification activities, to verify and validate the results of what each level of the new product development must be performed, all of that is again being accomplished as systems engineering will support it to make it happen. The diagram on the right-hand side is a classic example of, well, the bridge here does not have any electronics or software on it, but you can still see how when you're building complex big products here, for example, if you don't think of it beginning to end in one big single picture, you end up missing how the interfaces all connect together. And at the end, you can see the bridge is not meeting. And that's the whole point with that. So let's go forward with the next slide. What you're going to be seeing here on this particular slide is the V model as illustrated in the Automotive SPICE PAM 3.1. And for those of you who are familiar with SPICE, this is not going to be something new than what you are already seeing. So we're talking about stakeholder requirements that helps the systems engineering team come up with the system level functions and requirements. So you have system level requirements analysis process that we have here, which I will highlight with my laser pointer, which is sourcing this information from the stakeholder level input. This further can then be utilized as you get into the architectural design process, where you have the system architectural requirements. Typical way how we have architectural being satisfied include diagrams, and also something very important is interface level specifications. So interface level specifications, again, organizations do this in two different ways. Sometimes they might say there's the system level requirements, that's one single document. There's an interface level specification document that can again be a separate document. But at the end of the day, it helps connect the dots between the different blocks within an architectural diagram. So we'll also show you some example of that as we get into the subsequent slides. So with system requirements analysis, again, linking back to the systems architectural design, and then going back up in the V model on the right-hand side, you have the systems integration and integration testing process. Now, as you can see, the way it lines up with the architectural design, the main purpose with the integration process is to first put the elements of the architecture together, basically through the integration activity. And then once that has been done, you're going to perform integration level testing and that's what is getting accomplished right over here. So finally, going back up, you can see here the qualification level testing will be done against the system requirements analysis. And that's why you have the bidirectional traceability going again between the two blocks. Now, within the blocks, let me go into one more level inside it. You can see at the system requirements analysis, you have the system level functional requirement. And then from there, we have something called as verification criteria. Now, I put that there particularly just to emphasize the importance of that, because again, that's something that we typically see where organizations trying to implement SYS typically end up having some sort of deficiency or some areas that they need to typically improve. So verification criteria, and we'll talk about this in a subsequent slide, where the verification criteria serves as a mechanism for the systems requirements engineers to convey what type of verification activities should be done, and it serves as an input to the testing group. It's not meant to replace the test specification, but it's only an input to it. And from there, you can see how the bidirectional traceability requirement again drives architecture here, again going back to the system level requirements analysis process. So there's that bidirectional linkage there as well. And horizontally, you can see how test specification should be based on system architectural requirements. Now you can call it interface level functional requirement. There are different terms organizations use, but at the end of the day, we're talking about what does the architecture do and how is the interface between the architectural elements. That is what is being talked about right here. And then test specifications, where you have also test cases that need to be included into that. Now, test cases typically have a bit more detail where you're talking about how to perform the test. You have a step 1, step 2, step 3, that type of level of detail where test cases are going to be built. And test specification serves as a little bit more higher level that is connecting back into the requirement at the left-hand side of the V model. And then lastly, you have test results, which can include test records, logs, and the likes of it, showing that the test was actually performed, and you have results to prove which of them passed, which of them failed. So within the whole V model, the main important part of all of this is, where am I performing this testing, or where am I performing this requirements analysis? So the level of abstraction is important. So, and as I showed you in the previous diagram, where we had for more complex systems, you can have system having subsystem, and then you can have again subsystem. So again, you can have that multi-tier structure the way you want, depending upon how complex the system is. But at the end of the day, your V model will need to again correspond to what that level of structure is. So that's again something you have to consider as you implement automotive SPICE practices within your organizations. So here's an example that we have. So let's say I have a battery pack, that is the system in this case, and then let's say I have a subsystem, which is the battery management system, and then let's say I have the software below that. So I have 3 levels. Now I have a function in green, and I have a requirement in black over here. So you can see, for example, at the battery pack level, we're trying to ensure the vehicle transportation range is greater than 550 miles, which then translate, has a requirement saying that there's a satisfied range per a particular load specification, and you could have some type of load specification that can go along with it. So that's the specific requirement. Now, of course, you can have multiple requirements tied to one single function. And then as you go into the next level, which is a subsystem, you have permit charging, which will then support this particular function at the higher level. And then you can see fast charge to 80% capacity within the next minutes. That's again saying that that's what needs to happen to support what the battery pack needs at the higher level. And then when you go to the next level down from the subsystem, you're going to the software, where there's some state of charge calculation, SOC values being looked at. So the calculate SOC from a particular voltage reading per a conversion table. So let's say there's a specification table that's being referred to, which is being using to convert the voltage reading to the state of charge value, then that's again going to serve as an input into supporting what the fast charging should happen within the battery management system. So you can see how when you're going from one level to the next level, this chain of requirements that we have from top to bottom is going to support each other. Right now, I'm just taking one stream of function and requirement, but in reality, you could have one-to-many relationship, one function going to many requirements. And then again, from one level down to the next level, you could have multiple levels of multiple requirements again. Same thing when you go into the software as well, the same thing repeats. So with defining and structuring system requirements, just like we have all of this here, we are talking about having this traceability going back to the stakeholder requirements as well. Besides that, standard expectations on how you have the categorization of functional versus non-functional requirements. Non-functional, for example, reliability, cybersecurity, anything that sort of serves as a constraint within the system typically would be a non-functional requirement, whereas functional is pretty much what the system is supposed to do. So here, the battery pack should power the vehicle into providing X miles of range, for example. So over here, both of those should be considered. That SYS is not talking about just functional, but you also have to consider the non-functional requirements as well. And then, of course, there's some standard naming schema that you should typically have as you implement requirements engineering practices within tools out there. So, for example, while I use requirements slowdown module that we have within as part of our EWQMS tool, every project that we start off, we first set up what that naming convention should be for a particular project, and then at the system level versus the subsystem level versus the subsystem or the component level, wherever it is, you set up what that schema should be, and therefore any new requirement getting generated there has a clear identifier. Similarly, requirements management tools out there, again, all of them have that pretty much same capability. So again, having something of that sort is going to help you with ensuring and practicing bidirectional traceability as you get to the next steps. And the other part of all of this is structuring functions and requirements as part of a feature to support release planning and reuse. So if I have, for example, charging being a function, I would have related functions and requirements of what charging function should do or charging feature should do put up together so that I can reuse it between different programs. So I might be doing a program for General Motors, another program I might be doing for Rivian, or another program for Ford or Stellantis or any one of the OEMs. I could have some of those features that I can build as part of my platform, even that I could reuse between different programs, and therefore it makes it a lot easier for me to develop these different programs in parallel. So considering both reuse and release planning. Now, release planning is more about executing the project, where you have a timeline against which you're supposed to deliver these features. So for example, I have charging, and that's part of one of the earliest release, but let's say I have a diagnostics feature that only comes in much later in the project. That would be something that I have to plan against my timeline of the project, right? So that's, again, two things to consider there. Now, right up in the beginning of the webinar, I mentioned about how DFMEAs and other practices can also support the systems engineering thinking that we need to employ for SYS2, SYS3, SYS4, SYS5. So DFMEA is a very well-known practice that we have used in the automotive industry, picking the brain of some of my colleagues again, who actually within Omnex who serve in the board, for example, the AIGVDA, and the AIG 4th edition and SAE J1739 FMEA reviews, they have talked about how earlier, if you look at 4th edition, you're typically looking mainly at that particular focus level. But for example, when the newer FMEA approaches like the AIG BDA, you're talking about looking at the level it has in the higher, the information you have at the higher level and also the information at the lower level. So both are being considered. So how DFMEAs have also evolved to support the V model as time has gone by. So if you're talking about leveraging current practices, this DFMEA is a very good option as you're talking about analyzing system requirements. So very specifically, some of the expectations include correctness, technical feasibility, verifiability, and analyzing of risk. Those are 4 specific criteria SYS has laid out as part of analyzing system requirements. Now, talking about those individual requirements in detail. Now, verifiability is something that FMEAs have always had. If you talk about the controls, so you have preventive design controls and detective design controls that I have on my slide here, which very specifically talk about how verification is supported through DFMEAs. Now, this will be later used in DVPNRs, which we'll talk about a little later in the webinar today. So verifiability is covered there. Now, talking about the correctness and technical feasibility, now that's something that is typically analyzed as part of DFMEA itself, but some organizations choose to make it a little bit more explicit, where you could even get a sign off from the requirements analysis team against those individual functions and requirements that against correctness and technical feasibility that analysis has been in fact performed, and that there is explicit record capturing that those individual requirements are stated to be feasible and also are correct in the way that it has been defined. So DFMEA serve as a great tool to perform that particular analysis. Now, it's no new news that the DFMEA itself is a risk analysis methodology. So therefore, it's something that will again support that 4th criteria we talked about. So besides correctness, verifiability, and we have also risk analysis going there right along with it. Now, I showed you so this what I have on my screen is what we call as the 4th edition format that's been around for quite some time now. And with the newer AIGVD approach that is also now, that is now being rolled out into the supply base by the OEMs, automotive OEMs, you can see how we're talking about 3 levels here. You have the function at the focus level, function at the higher level, function at the lower level. Similarly, you also have requirement at the higher level, requirement at the lower level, requirement at the focus level, of course. And then you can also have failure analysis that is being done at the 3 levels as well, which will then become the effect at the higher level, the cost coming from the lower level, right? So you have all of that coming together into one single frame here. So AIGVDA is supporting that thought process. Now, I have this at, let's say, the battery pack that I showed you in the beginning. Now, that's at the system. How about the subsystem? The same thinking can be again utilized as you're getting into the subsystem level. So here you have from the battery pack, I'm going into the battery management system. So from one level to the next. And then subsequently, I can employ the same practice going downstream into the hardware and the software as well. So this is a perfect example of how FMEAs can support risk analysis across the V model. And also in a good way, you can practice system requirements analysis part of it. That specific BP that SYS2 has as an expectation for organizations implementing SYS. Really, FMEA has a good solution there. Okay, So that's something for us to really consider. Now, going into the next slide, we're talking about a P diagram. Another expectation within ASPICE is about analyzing the impact on the operating environment. So I have a system, and how do I analyze the impact the system has on the operating environment? Now, when you get to the software process, which we won't cover today, but it has a similar expectation. Now, how does the software have an impact on the operating environment it has? So here within the system, we're talking about utilizing a P diagram, and the P diagram is meant to support the analysis that the system will have on its operating environment against noise factors, against signal factors, you have responses, you have control factors, and error states. So basically what we are doing here is we are taking the architectural diagram, putting it right up in the center, and we're saying, what are the signal factors that serve as inputs going into this? And then I'm getting responses as outputs. So you have inputs and then you have outputs. Now, to this, what type of noise factors also impact all this? So that's the other one that we have coming from the top. And then now, what type of control factors help with all of this? That's the box to the left-hand side here. And then tied to the responses, you have the error states that the system can go into as well. So when you look at the P diagram, you can also considering extending the following relationships from the P diagram to the DFMEA. So responses can tie into the design functions, where error states can tie into the design failures, and control factors can tie into the design control methods. So this way, P diagrams and DFMEAs can have that strong linkage between each other. In fact, that's one of the principles we've implemented within ACOPRO and how requirements slowdown functions together, that there is that exchange going back and forth between the P diagram and also to the DFMEA if you choose to do that. Now, of course, this is optional. So there are organizations that sometimes do not want to do it, and they would just decide to keep what's on the P diagram separately, and then the DFMEA would look at it, but they wouldn't really source that exact same data, but they would just consider that as an input. Now, but on the other hand, if you can definitely have that readily made available, life becomes much more easy, right? So that's a strong linkage you can have again between P diagrams and FMEAs. Further expectations within the system requirements analysis process go into verification criteria. So we talked about this very briefly in the start, but I mentioned verification criteria. They are not actually what we call as test cases, but they serve as an input into creating them. And typically it's done by the requirements engineering team. Now, recently, this came across during one of my discussions with an organization that we are helping implement ASPICE, where they mentioned, okay, verification criteria is being created by the requirements engineering team, but testing team has a totally different idea of how the verification methods can be employed. Now, how can we make it more effective? So yeah, I mean, the simple solution is to perform a cross-functional review so that the testing team can also give their inputs and also use that event as a opportunity to confirm that the appropriate verification methods have been specified. So with ASPICE, the verification criteria, they have a very clear cut definition of what it should cover. So in the Automotive SPICE guidelines, the first edition that came out in 2017, it clearly states out what is expected as part of verification criteria. Now, of course, the first one we're talking about is identification of the requirement to be verified. Now, if you have a very clear traceability going between the requirement and also the verification criteria, so it could be as simple as having it documented into the next column what the requirement is already documented to. So I have the requirement and the verification criteria in the very next column right next to it. So that's an easy way to correlate that this is the verification criteria that this requirement is tied to. We could also have verification method that clearly states, okay, this is how I'm going to be doing it. So this could include inspections, peer reviews, audits, walkthroughs, analysis. Like at the system level, for example, think of them as methods like you have environmental testing, reliability testing. So again, very you can see again some of the parallels coming out from DFMEA there. You have the controls. What type of detective controls are we talking about? Or in some cases, we're talking about the preventive controls too. So what type of preventive controls are being talked about? Verification environment. Let's talk about that battery pack example. If you look at electric vehicles, typically we encounter challenges where in extreme winter, what type of range are we getting? Like we talked about the 550-mile range, for example. Am I getting that 550 miles in an environment that has extreme winter conditions? Preconditions and special conditions, where is there a specific state that the system must achieve before this can be tested? So only maybe in an active state, or maybe after switch off and after a certain period of time should I be testing it? Or maybe only after we switch on and after a certain period of time should I be testing that? So all of this serves as an input into what the preconditions and the special conditions are. Constraints, any limits on parameters, like what are the high, low limits, constraints? Again, non-functional requirements sometimes can support this definition of what a constraint should be. So that is again something to consider. And then of course you have the success criteria. At the end of the day, what was it supposed to be? Am I supposed to get 5 volts of output from a system? If so, yeah, then am I getting the 5 volts? That's something to consider. So success criteria along with constraints, preconditions, verification environment, method, and also clear linkage back to the requirement is something that is essential when we talk about verification criteria. Now, we talked about how establishing bidirectional traceability is very important across the V model in a SYS. And also, if you look at similar standards like functional safety, cybersecurity, and the likes of it, the same expectation continues. So we're talking about having the stakeholder requirements that can go into the system level functions and requirements, and then from there to the subsystem level functions and requirements, from here to here to here, and then to the software. Then you can go into the software module and then to the software unit. So we're talking about traceability across all of this that you can clearly see and identify. And also the term bidirectional traceability indicates you can also be making changes at the lower level, but it has to be flown back up to the top and making sure that at the end of the day, let's say if I'm developing a particular software unit, there's still at the end of the day, I'm doing value added engineering, and there's a stakeholder requirement I can trace all of this back upwards to, and it's not something that I'm just creating or I'm not adding any. For example, in SYS, when you look at the architectural process, they talk about resource consumption. So when you're talking about resource consumption, you're talking about, do I have junk code or junk data that I'm adding onto the overall software that will again drive how my resources are utilized? So am I adding more memory to all of this? Do I need to now upgrade to a different chip than what I had already planned to, because now my software is bigger in size, right? So all of these are things you have to, again, consider. Going forward. So again, we're talking about bidirectional traceability being represented in a different way. Here you can see how all the way from the lowest level requirement, we are tracing it back up to the top. So here you have the requirement all the way. This is a hardware example where all the way from the bottom, you can trace it back up into the system as well. So there's that linkage going back from bottom to top. Now talking about architectural design, so we're switching from system requirements analysis into the architectural design. So the architectural diagram in SYS, you have expectations for both static and dynamic architectures. So let's talk about that. Here we're saying the architectural diagram is a block diagram that is traditionally completed before a DFMEA is completed, right? But so it doesn't mean that, you know, is you do one later and then because in the V model, the architecture sort of comes below that. It's not that you're not looking at it at all when you're doing the DFMEA, but you could typically do the block diagram and then perform the DFMEA to do a more effective analysis there. Because that's typically a precondition. Whenever you're doing DFMEA, the first thing you start off is what are the boundaries, defining that block diagram, and then you're coming up with the DFMEA on that, right? So the block diagram pictorially represents the product and its internal and external interfaces. When completing a block diagram at a system level, it needs to show all the elements in its next level of structure or the BOM. Also, you can look at, for example, SysML diagrams that you could leverage into deciding appropriate architectures for the system. So here you can see where you have within SysML diagrams, you have behavioral type of diagrams, structure type of diagrams. So these are more of your static diagrams, and these are more of your dynamic diagrams. So going off by a simple example, right upon the static architectural diagram, here you have a block diagram for a battery pack system, and then you have another one which is a block diagram for a standard 32-bit MCU. So you can see how in both scenarios there are blocks that represent, first of all, the big blue box is representing what the whole system is. So here's the battery pack, and here also you can see it's a 32-bit MCU. So that's the big blue box. Now within the big blue box, you have the smaller boxes that are representing the next level within the hierarchy. So you have the battery management system, and then you have the hardware and software inside that. Similarly, you have the battery module or any one of those other elements. So there are boxes within boxes, right? That's the next level. And then you have lines going between the boxes. So what the lines represent are what we call as interfaces. So, and the same pattern follows here too. So typically, this is what you would have in static architectural diagrams. And when you look at interfaces, we are talking about interfaces. So we've listed out some examples from the AIGVDA handbook that details out what interfaces are. So we have, for example, physically touching interfaces, energy transfer, information transfer, material exchange. So these are, again, some examples of what interfaces are. Now, in addition to that, you could add more types of interfaces. Custom interfaces can be added and used within different projects. So again, this is an example deck, but of course, you can have your own set of interfaces for different projects. Talking about architectural diagrams that are dynamic in nature. So within this figure, we're talking about a dynamic architecture. So the name dynamic itself gives you that perception something is changing, right? What is changing? Something is changing with respect to time. The state of the system in this case is changing with respect to time or certain scenarios. So for example, here we're talking about a state machine diagram for an isolation monitoring function of a battery pack. So it starts, then it goes into the startup state, and then in the startup condition, it first checks for monitoring of isolation. So in an electric battery pack, you want to make sure the isolation is working first before all of this starts up, right? Because again, we're talking about high voltage scenarios, and you don't want safety related issues taking place. So that's an initial check that is performed as you start up the vehicle. So you monitor for isolation, and then if it's an okay condition, you go into running, and then when you switch off the vehicle, it's in shut down, and then you again do the monitoring for isolation. And then if at any condition you reach a not okay, so for example, when you start up and you monitor for isolation and you get a not okay, then you issue an isolation violation, and then you power shut off, and then you have to notify servicing, or that's the next step to take place, where this will have to be investigated and then resolved before you go into any additional next steps. right? So this is, for example, a dynamic architectural diagram that is representing a safety-related function. Now, as you consider these architectures, one thing you have to also consider is how I'm going to take my functions and requirements that I did in SYS2 and then allocate it to the architectural elements. So I have the architectural elements right up here at the top. So from the battery pack, I had a battery management system, a module, a mechanical enclosure, and a module balancing unit. So I had these elements to which I'm going to be allocating my functions and requirements. So basically, I take a function requirement and allocate it and say, yep, this one applies to this subsystem, or this one applies to this subsystem. So you can indicate it so that it's flown down. And this is what we call as requirements flow down from one level to the next. So that was an example of how allocations are done into the static architecture. I'm also including a different concept here on my screen where we're talking about allocating functions and requirements into your dynamic architecture. So this is a example consistent with the previous architecture that I just showed you in the previous slide. We're talking about isolation monitoring. So let's say I have isolation monitoring to a particular X mega ohm. So let's say 400 ohms or something like some resistance value. So in the operating mode 1, I'm not going to be checking for that. But if I'm going to operating mode 2, or like, for example, if it's an off condition, I'm not checking for isolation monitoring. The moment I'm going into a low energy function or a high energy function, that's when I'm going to be checking how my isolation monitoring is going to perform. So, you can see how this particular function requirement applies to this particular state of the system. So this is like a mapping being done there, where you're mapping the function and requirements against a particular dynamic architecture within the system list of architectures. So just another example right there. Talking about when you run into a scenario where you have multiple architectures for a given system, how do you pick the best one that applies to your system? Like, I have a few different options here. What is my best one that I should be going ahead with? So to answer that question, here's one classic example of something we can already leverage from your automotive practices that you might be already doing today, a decision-making worksheet that you could utilize. So in the decision-making worksheet, we're talking about what's my end result. My goal is to select the architecture for system ABC. And my available choices, which serve as criteria, I have architecture 1, 2, 3, 4. I have 4 different architectures. Now you document something called as givens. Givens can be thought of as like the must-haves. So it needs to follow, let's say, AutoSAR. So if AutoSAR has to be followed, then you're saying architecture 1, yes, it follows. Architecture 2, yes, it follows. But when you get to 3, it does not follow, therefore it instantly rules out for you. And therefore you don't need to consider it further in your analysis. Now, when you go to architecture 4, this one again follows AutoSAR. So that's your fourth option, which again, you can consider for the next step. So when you go to the next step, you're talking about your wants. So these are your nice to haves. So you have modularity, reuse, development effort, and development cost that you're considering. So now when you consider these factors, which you have listed as wants, and you're listing out how important this is to you, this is you giving your weightage against these points. So you're saying modularity is most important, giving it a rating of 9 out of 10, whereas development effort and cost are the second most important with a value of 8, and reuse is at number 7. So in this way, you can list your score against each one of them. So for example, you're saying how good, you can say for this one, I'm getting a 6, 7, 9, 9. Here also, here I'm getting a 6, 10, 9, 8. And then through a cross-functional review, you can come up with a consistent scoring that can multiply with how important, with how good it is, and then you can say this is the best option that I'm going with. So this is my best architecture that I'm selecting out of the options. So when you talk about integration and integration testing, and also the qualification testing process, so I grouped that together here mainly because the expectations in ASPICE largely are similar, but the main difference is the context in which you apply. So although if I'm saying, develop test cases, when it's at the system integration and integration test level, we're talking about developing test cases against the test specifications that map up to the system's architectural requirements. Whereas when I'm in the qualification level, we're talking about the test cases that trace back to the system functional requirements. So that's the key part here. What level am I talking about, right? So with all the testing processes, something that ASPICE really calls about and is very important is your test strategy. So test strategy is an important document that defines the scope of what will be tested where and within what rules. Simply put, if I'm in the system integration test strategy, it shall describe what is performed at the integration testing level, while I'm at the qualification test strategy, testing level, I'm talking about what is performed at that qualification level. So the scoping is a very important activity, and sometimes people get these mixed up and they combine the multiple processes, and then it's not very clear what test specification is tracing back to either the system level requirement or is it to the architecture. Same challenges can also be seen when you talk about the software processes as well. So this is a common issue that we can typically see across the board. So if a portion of a testing is being performed by your customer, that's also something you have to consider in your test strategy. So you have to clearly say what is within the scope of testing done by your organization versus what your customer is going to be doing, so that there's that level of separation and clear scoping you can put forward. ASPICE offers recommendation on what should be covered in a test strategy. If you go to work product 852 test plan, there are clear work product characteristics that it lays out. And additionally, there's the ISO 29111-119-3 that also gives you further details into what test plans should cover. So those are typical formats you can follow. But having said that, one option that you could use here is the design verification plan and report. I also added the term or validation also because it talks about what level am I doing my DVPNR at. You might be wondering, when I say what level is a DVPNR? Yes, we're talking about in a V model. When I'm at like a subsystem level, I could have a DVPNR there at the subsystem level. I could also have a DVPNR at the system level. Within my V model, wherever I do have my requirements captured, against that level, I could have my DVPNR. So that's, again, something important to consider. So the design verification plan and report, so DVPNR, you have your two main sections. Right up at the top, you can see this is the test plan, this is the test report. So within the planning, you have all the planning related information. And then when you get to the test report, you have the results of execution, that so many samples were tested, did it pass, what is the past result, actual results, all of that being captured there. So with that, DVPNR again becomes an important tool that you can leverage along with your DFMEAs. Now, strategy and integration sequence. So this mainly applies to the SYS-4 process rather than the SYS-5, which is a systems integration testing process. That's where this becomes more important, the one slide that I'm showing you right now. So when we're talking about integration, we're talking about taking your individual blocks let's say it could be the subsystems that you're putting together, and then you're building the overall integrated system. So a definition of how the level of complexity regarding the product and organization is handled, like for example, if you have multi-site development, technical complexity of the system, all of those factors being considered. And if you have, one subsystem being developed elsewhere, another subsystem being developed elsewhere, you're talking about how does it all come together, the integration steps and sequence before you come up with the final full system. So even within one development site, of course, you have different levels where the components of the system can be integrated. There's a specific sequence to be followed. That's what we're talking about, integration steps and sequence there. So the diagram is typically included into your strategy document wherever you're doing system level integration, and that's something that is typically looked at. Definition of test cases. Now here we have IEEE 829 test case specification template. Again, a recommendation from SYS that we've used to show what test cases should typically cover. So here we are talking about some type of identifier, what test items cover, what will be tested, features and conditions to be tested, input specifications, output specifications, environmental needs, any special procedural requirements, intercase dependencies. Does it, ring a bell? Doesn't it look similar to what we have in verification criteria? Because yeah, there are aspects of verification criteria that you can leverage as you create your test cases. Keep in mind, those are two separate things, but you can still use a lot of the information in your verification criteria as you're coming up with these test cases. So both of them do make that a relationship between one another. And then, of course, the selection of these test cases, as you consider, it should be in line with what your release plan is showing. So for example, if I have a feature that must be released in, let's say, June 2023, I must see that the test cases that map up back to that particular feature should have been tested, and I should see results of pass as I'm looking at what is coming out in June 2023. So if there are, let's say, failures out there, it should not be something significant, or you should get probably something what we call as like a customer waiver into certain feature that you're still delivering with, let's say, a defect. We're talking about during development stage. We're not talking about start of production where it's already design freeze is done, everything is finalized, and later you're going in. That's not what we're talking about. We're talking about the earlier stages of development, while you have intermittent releases, and then maybe you do come across a bug, but the point is that's not critical. It doesn't affect safety, or and you have a bug fix that is planned in a later release. So those kinds of things you will have to very clearly trace it back into your release plan, and also show records of evidence back to all of this. Tying back the FMEAs and the DFMEAs and how it will support you with the traceability and consistency. So here, remember this diagram that I showed you almost at the beginning of the presentation, how when we covered system requirements analysis process, we talked about the DFMEA. Now you have the DFMEA at the system and the subsystem level. So how will you trace it back to the DFMEA? Simply, at each level, you can have a DFMEA that traces back from the DFMEA to the DFMEA. Similarly, here as well, you can have at the subsystem level, you can have a DFMEA that will trace back into the DFMEA at the subsystem level. And in fact, the screenshots that I'm showing you from Aqua Pro is what it does. And that's how we can show that across the V model, we have that linkage going back and forth between both the sides. Lastly, to summarize what we looked at, systems engineering can be leveraged to effectively bring collaborations between the different development domains being system, hardware, software, mechanical, chemical, all of those different domains coming together, how you can leverage the systems engineering thinking there. Existing practices within the industry that include DFMEAs, DFMEAs, P diagram, interface function metrics, and more can be leveraged to effectively practice systems engineering within your organization. So It's not that you have to reinvent the wheel, but you can already use some of those good practices that are probably being done in your organization today anyway, and then leverage that for your subsequent need. And then you have later similar practices in systems engineering can be reused into software engineering as well. Because if I'm talking about DFMEA, it's a risk analysis approach that you can also do what we call a software FMEAs. You can do the same thing there and analyze the risk in your software right there. With that, I would like to re-emphasize the 7 levers that we talk about from Omnex. We talk about the 7 levers of the automotive industry, that a lot of rapid changes have been happening, especially within the electric and autonomous vehicle sectors. So you have the IATF 16949, ISO 26262, automotive SPICE that we covered today, supply chain practices, sort of cybersecurity, agile APQP, all of which Omnex we do help our customers with gap analysis, training, personal certification, implementation coaching, engineering design services and software solutions, assessments and audits, and product certifications. And talking about implementation coaching and also training, we do have some of the upcoming public training activities that are coming up. So you have the following INTAX certified ASPICE courses and non-INTAX ASPICE courses as well, that we can do on site, and also you can join one of our open enrollment courses that we do for multiple customers. And you have ASPICE courses. It's a big list. Here are all of our functional safety courses. Again, the list continues in page 2. SOTIF and Agile series courses, AI, GVD, FMEA courses, cybersecurity training courses, and a lot more that you can find in our website, omnex.com, or you can refer to evav.omnex.com as well. Both sites contain the information from our various training practices. Now, with that, I'm going to request if there are any questions and answer them in any of the topics that we have covered. If any of you have any questions and would you like to hear any more further clarifications of information, I would be happy to help out with that. Okay, one of the questions I have here tie into doing system. So we have system level FMEAs and subsystem. Can I do the same thing at subsystem? Yes, absolutely. You can perform FMEAs also at the subsystem level. There's nothing stopping you from doing that. Just like we showed with the system, subsystem level, you have the FMEAs. You can also have the DVPNRs also at the respective levels. So both will help and support you with what you have to do there. So yeah, absolutely. The answer is yes. Okay, any recommendations on approaches for FMEA methodology? So it largely is a customer-driven approach for some organizations, or in other organizations where the top management itself is saying, yeah, this is the recommended approach that we're going to be taking. But while 4th edition has been a long time favorite for FMEAs, we've seen how because of customer requirements from some of the automotive OEMs, there has been that shift from the current approach going into the 3-tiered, or let's say multi-tiered structure of AI GVDA, where at least you have a higher level and at least you have a lower level component, and then you're analyzing the risk across that structure. So that's that, you know, again, depends upon whether it's an internal decision or something coming from a customer. But yeah, those approaches can be utilized. And of course, you can learn more about that if you would like to from one of our open enrollment or on-site training classes that we can do for you. Yes, and also the thank you. I also got a note from my colleague about the SAJ 1739. You're absolutely right. There's also the SAJ 1739 that can also be leveraged as well. Yes. Yes. So question on requirements management tools. Yes, there are many requirements management tools out there that help you with that same. One important thing to consider in all of this is the template that you decide and structure for that particular process. So for example, I would have a template when I'm starting off a project. Typically what I do is, or anybody who does it, in most development projects, they would come up with a structure for what the columns and data within each column should contain. So I have a structure, I have an identifier, let's say like a numbering schema, there's a function, there's a requirement, there's also the links going back to the next level of requirements. There's some verification criteria I would capture again. We could also capture test instance status if you want to capture all the way from your DVPNR back into the requirements document. If you want to show that, some tools do offer that capability where right next to the defined requirement, you can show the results of the latest execution of the test. So it becomes very easy to see. Last time the test was run, it was a pass. Sometimes it has not happened. So yes, there's a question on systems architecture design. Any other tool? Rhapsody is one. Definitely there's the EA tool, Enterprise Architect. I know JAMA has some of their own tools as well. And really, from an ASPICE point of view, there's no constraint that you should only be using one of these architectural design tools or not. You could even use Visio, PowerPoint, any one of those. The only thing is that, if you have a linked architectural design tool, it becomes a lot more easier to maintain and also to scale. Whereas with standalone architectural tools, like, if I'm doing it on a Word document or on a PowerPoint, something like that, then, the linkage capability is a little bit more manual in that case. So yeah, there are tools like EA and Enterprise Architect and the other ones that you can leverage as well. All right. Regarding training, yes, I think the best place to refer to is back on our website. You can refer to omnex.com, where you will have the latest list of courses, the schedules for training, upcoming training events, all of that being listed out. So you can refer to that as well. All right, now with that, I think we are done with no more further questions I see on the board. So again, please reach out to info@omnex.com if you need any help from our side. If you have any questions, we'd be happy to help you. So reach out to info@omnex.com, and thank you for attending the webinar, and you all have a good rest of the week. Thanks.